Right, so we're ready to start. Welcome, everyone. My name is Ihor Dvoretsky. I'm a developer advocate at Cloud Native Computing Foundation. And today we're here with Caitlin Barnett from the Linux Foundation and from Cloud Native Computing Foundation, who is helping us with hosting the webinar. And we have two presenters today, both representing Google and storage special interest group at Kubernetes community. We have Saad Ali, who is a SIG storage lead, and Michelle, who is a SIG storage member at Kubernetes community. And today we'll speak with you about Kubernetes 1.10, the latest release of Kubernetes, the major highlights about this release. And Saad, together with Michelle, will highlight two most major and prominent features that have landed in this release. So Kubernetes 1.10 is the first release in the current year. We have 25 new features landed in this release. For those who've been following the previous releases, the previous release announcements of Kubernetes, you could notice that the number of features in the current release is a bit lower because usually we had around sort of 40 features. But the reason of having only 25 features is that community has been focused on enhancing the existing features from the previous iterations, comparing to developing some extremely brand new functionality. At the same time, we had a few major areas where the community has been working on during Kubernetes 1.10 iteration, including workloads, security, and storage enhancements. And today, Saad, together with Michelle, will focus specifically on the storage enhancements that we have today with Kubernetes 1.10. Saad, please go ahead.
Cool, thanks, Ihor. So in the storage SIG, we've been working on a number of features this quarter, mostly moving features that we started on in the last year, moving them to beta. One of those features is the container storage interface, which I'm going to talk about. Another feature is local persistent storage, which Michelle is going to tell you more about. We also had ephemeral storage resource go to beta as well this quarter. So let me jump in and explain a little bit more about CSI. As I mentioned, CSI is beta in 1.10. It was introduced as alpha in the 1.9 release, which was last quarter. So let me refresh your memory about what the problem is that CSI is trying to solve. The Kubernetes Volume plugin system that you're probably familiar with already is very powerful. It makes it easy to consume block and file storage, but it's been challenging to add support for new in-tree volume plugins with the existing volume subsystem because it requires checking plugin code into the Kubernetes core repository. And this is painful for a number of reasons. This means that storage vendors who want to extend the Kubernetes to support their storage system have to align with the Kubernetes release process. They have to, even if they want to do just a bug fix, they have to align themselves with the Kubernetes release process, which can be daunting. For this reason and a number of other reasons, we've wanted to have a mechanism by which volume plugins can be added to Kubernetes completely out of tree. Along came the container storage interface, and this was a collaboration between not just Kubernetes, but other cluster orchestration systems, including Mesos, Cloud Foundry, and Docker. What we realized is that there was this need across the industry for a standard that would enable us, the container orchestration systems, to expose arbitrary storage systems to our containerized workloads. And storage providers, storage vendors also wanted to be able to have one standard to which they could design a plugin for and have it work across all COs so that they don't have to re-implement it for every single orchestration system. This specification was started, work on it started last year in February, and the 0.2 release has just been cut. That should say February 2018, not 2017. And the specification for the interface has been published at GitHub. It's open source. You can collaborate on it at the specified URL. But the specification alone is just an interface. We need to go and actually implement it to make it usable to our users. And that's what we've been working on the Kubernetes side of things, where with the addition of support for CSI, Kubernetes becomes more extensible. We can have new volume plugins that can be deployed on top of Kubernetes without ever having to modify the core Kubernetes code. So then the next question is, well, how do I use a CSI volume? The good news is that you use it in exactly the same way that you're familiar with using existing volumes like GCPDs, empty DIRs, NFS. First of all, there is a storage class. In your storage class, you specify, you point to the CSI driver as your provisioner, and you pass in any parameters that you want to be passed in when a new volume should be created. Think of this as a template for creating a new volume. And when you want to create a new volume as an end user, you will create a persistent volume claim. This is the exact same persistent volume claim that you're used to. You should point to a storage class that will provision a CSI volume. In this case, fast storage that we created up above will result in a CSI volume being provisioned. And then you can use it in your pod in exactly the same way. In the volume section of your pod specification, you specify persistent volume claim, and the claim name corresponds to your PVC. And of course, you can still pre-provision a volume if you want to. For a CSI volume, you can manually create a persistent volume object. This is normally done automatically if you're using dynamic provisioning through PVC and storage class. But if you don't want to use storage classes, you want to pre-create your volumes, you can do that by creating your own persistent volume object. And in your specification, specify that it's a CSI volume. Specify in the driver which driver it is. The name of the volume is the volume handle, and additional attributes that are specific to that volume. So we're moving to beta this quarter, and you might be wondering what's new in beta. The big difference is that CSI is now enabled by default. You don't have to opt in, as was the case with alpha. And we're also snapping to the 0.2 release of the CSI spec. The 0.2 release has a number of breaking changes from 0.1. So if you had a 0.1 driver, please make sure that your driver has been updated before you use it with Kubernetes 1.10. And then we had a bunch of features go in on the Kubernetes side of things, including mount propagation, which is a dependency for deploying CSI drivers. That feature has moved to beta. We've also improved security around the volume attachment objects, which are required to attach and detach CSI volumes by reducing which volume attachment objects a particular node can access. It can only access volume attachment objects for the volumes that are scheduled on that node. We've also improved secret support for CSI. So each of the different CSI calls, now you can specify the secret associated with it in the CSI persistent volume source object. You can also specify the file system type. It used to be hard-coded to ext4. Now that's customizable. We also added in a new call into CSI that's called node stage volume. This corresponds, if you're familiar with the Kubernetes volume subsystem, the mount device call. And what this enables is basically a local attach operation, if that is relevant for your volume plugin. So what's next? We're going to try and target GA for CSI, not this coming quarter, but the quarter after that in the V12 release, 1.12. Before we get to GA stable, some of the features that we want to tick off are block volume support. Currently, CSI only supports file. We also want to add in support for a generic mechanism to be able to specify availability topology. So this is things like zones, racks, regions. Storage may not be equally accessible across the entire cluster, and we want to introduce a mechanism to be able to represent that in the CSI interface, and then for Kubernetes to interface with that to do a couple of things. One is to be able to schedule a workload smartly. So if a volume is constrained to a particular zone, make sure that the workload using that volume also lands on that zone. And then also make Kubernetes smarter, something that Michelle is going to be working on in the future, by having the scheduler influence where volumes are going to be provisioned. Today, where volumes are provisioned is either random or it is controlled through the storage class by the cluster administrator. But we also want to allow the scheduler to be able to influence that, so that volumes can be scheduled on to nodes that have availability rather than randomly. We also want to integrate with the kubelet device plugin mechanism. This is something that the GPU team has been working on for a while. We want to have a standard way by which plugins are added to the kubelet and registered with the kubelet, instead of having a different mechanism for every different type of volume or every different type of plugin, whether it's GPU, device, CSI, and potentially even networking. So we're looking to achieve that consistency. We're also starting to work on introducing snapshotting into the CSI interface and then bubbling that up into Kubernetes. And a call to action: if you're a storage vendor, you're interested in having your storage system exposed in Kubernetes, now's the time to start developing CSI drivers. Reach out to us if you need help. We're happy to help you, and please provide feedback. We want to make sure that this thing is actually useful for storage vendors. We have a handful of drivers that we've been testing, but we'd like more. And all of this material that I just went over is going to come out in a blog post on kubernetes.io today, so keep an eye out for that. And with that, I'm going to hand it over to Michelle to discuss local persistent volumes.
Thanks, Todd. All right, so I'm going to talk about the local persistent volumes feature, which is now in beta in 1.10. So to give a brief overview of what the feature is, this basically allows you to specify a local disk as a persistent volume using the existing persistent volume interfaces that we have today. This feature is most useful when you use it in conjunction with stateful sets and the volume claim templates that stateful sets provides. Basically, each replica in a stateful set will be able to get its own volume, or local persistent volume for each replica. Alongside with this feature, we made a number of scheduler enhancements so that the scheduling of local disks is smarter. There's two main benefits of this. First, if you have a pod that uses a local disk, it's going to always get scheduled to the node where that local disk resides. That's what we call data gravity. That way, if the pod has to restart and be rescheduled, it will always land on the node where your data is. The second aspect of this is that we make the initial persistent volume claim binding smarter. So previously, how persistent volume binding worked is that you would create the persistent volume claim, and then we would randomly pick a suitable persistent volume for it. So what could happen with local volumes is we could end up picking a local volume on a node that doesn't have enough resources to actually run the pod. So as part of this feature, we added enhancements into the scheduler to be able to postpone that initial PVC binding, so that the scheduler can look at all of the pod's other scheduling constraints, such as the resource requirements, any affinity or anti-affinity policies, any taints on nodes. And then also consider the PBC requirements at the same time, so that we can actually bind the pod's volumes to a node that can actually run the workload. So before I proceed, I first want to point out there are a number of caveats with using local storage or local persistent storage. First is the data gravity part. So your pod will always get scheduled to the node where that local disk is, but that also means if the node has a problem or the disk has a problem, then your pod is also stuck. Another challenge is that now, because your pod must be scheduled to that specific node, it has to be able to fit on that node too, which means that if for some reason your pod died and then in the meantime some other pod became scheduled onto that node, your original pod may not be able to fit anymore when it gets rescheduled again. In addition, many local disk products in many cloud providers have lower durability guarantees. I think for most of the major cloud providers, the local disks will basically, you'll lose all the data in the local disks if the node gets some sort of error. So for all of those reasons, local persistent volumes is not suitable for most workloads. I think most workloads should stick to the distributed and highly available storage solutions out there today. However, there are a few workloads that are still suitable to use local disks. Those workloads have to be able to tolerate node and data unavailability and potentially data loss as well. Some examples of such workloads are workloads that want to cache some state to SSDs for improved performance. And in those kind of workloads, they're potentially caching so much data that it can't fit in memory, so they'll have to go to SSDs instead. They want the data gravity in order to avoid having to reload the entire cache from scratch whenever a pod has to restart. The second major use case is for distributed storage systems that will shard and replicate data across multiple nodes. That way they can tolerate having a node go down and potentially recover from that. Examples of some distributed storage systems would be like MySQL or Postgres, Gluster, Cassandra, and so on. There's quite a few that can fit in this bucket. All right, so how do you actually use this feature? There are 3 easy steps. The first 2 steps are done by the cluster administrator. First, the cluster administrator has to create a storage class for the local disks. Then the cluster administrator has to create the local persistent volumes that are available in the cluster. Once all that setup is done, then the user can go ahead and now create stateful sets with their persistent volume claim templates. And then they will start binding to the local PVs that were created. The full and complete documentation is available on the Kubernetes website, but I'll go over a brief example now. So the first step, create a storage class. This is needed so that we can enable the smarter scheduler feature that I was talking about earlier. Basically, by default, persistent volume claim binding occurs immediately once you create the persistent volume claim, but we actually want to delay that initial binding until a pod is actually created that uses it and can go through the scheduler. So to enable that option, to enable that mode, you have to add this new volume binding mode field into the storage class that you are using for your local storage. And one important note to take into account, normally storage classes have been associated with dynamic provisioning. In this initial beta offering of the local persistent volumes feature, we don't support dynamic provisioning yet. You still have to manually, or you still have to create the persistent volumes ahead of time. But we still need to define this storage class in order to trigger this new scheduler mode. All right, so now the next step, which is to create the local volumes. There's two ways you can do this. You can either do this manually, one at a time by hand, and there's a more automated way that I'll also describe next. But first, I'm gonna go over the manual way to create the local PVs. So you'll see here, this is my example persistent volume spec. And I've highlighted the two new major fields that need to be set. The first field is the local volume specification. And it's pretty simple right now. The only field is a path, and this is the path to the global mount point of this volume on the local node. Like I mentioned before, this disk has to be pre-formatted and mounted globally on the node beforehand. And also for this manual creation process, we only support the reclaim policy for now, which means that when your application is done with the volume, someone needs to go in and clean up the local disk and then recreate the persistent volume for it. The second new field that is available now in the persistent volume object is node affinity. So this is very similar to node affinity in pod objects today. The only difference is now we're applying it to a persistent volume. So what a node affinity on a persistent volume does is it restricts the nodes that this persistent volume can be accessed from. So in the case of local volumes, we want to restrict this persistent volume to only be accessible from a single node. So we do this by specifying the Kubernetes hostname label key, and the value of that key will, in this example, is my node. So my node in this example is called my node. But you would, put in whatever the actual node name of your in your cluster. So this is also, so we're using this right now initially for local volumes, but this node affinity can be expanded in the future and is flexible enough in the future to support any other volume type. So if you have storage, if you have a volume type that is restricted to specific zones, you can also use node affinity to specify that. If you want to restrict your storage to specific racks, you can also use this as well. All right, so like I mentioned, one downside here of manually creating the local volume is that you need to manually clean it up and recreate it when the application's done with it. It's kind of a pain. So to improve on that, we've implemented this local volume manager that you can run as a daemon set in your cluster that will manage a lot of this PV lifecycle for you. You still have to pre-format and mount the local disks first, but you can mount it into a predefined directory on your node. And when you launch the local volume static provisioner is what we call it, it's going to look under those, it's going to look for mount points under those pre-configured directories, and it's going to automatically create the persistent volumes for you. And then when you end up releasing those persistent volumes by deleting the persistent volume claim, the static provisioner is also going to automatically clean up the disk for you and delete the persistent volume object. And then it's going to repeat the cycle, and it's going to find a new mount point again that doesn't have a persistent volume for it, and it's going to recreate it. So I would highly recommend that you use this provisioner here, static provisioner. It's not a dynamic provisioner, but I would recommend you use this to ease the lifecycle management quite a bit. So that covers the second step of how you can create local persistent volumes, either manually or automatically. And the third last step is to actually use them in your workloads. So luckily here, for this step, the process is exactly the same as it is today. You use the existing volume claim templates that's available in stateful sets. You use the same, you request storage capacity and you request specific access modes. The only difference here is now you need to specify the storage class name for the local storage that you created or that the administrator created earlier. And after this, the whole workflow is exactly the same. You could even easily do things like switch between using local storage and switch between remote storage just by changing the storage class field. So that's the basics of how to actually use the feature. And you know, we're still there's still lots of other work that still needs to be done before we can go GA. Some of the items that we're currently focusing on now are to improve the local raw block volume support. It's available right now in alpha in 1.10, but we'll have to push that to beta as well. The second major feature that we're working on is supporting dynamic provisioning using LVM. This is also still going to require more scheduler changes and also more provisioner changes on the local storage front. So that is in active development. And the third step, like I mentioned, is to try to automate more of this node setup work. So I previously mentioned that you still need to manually format and mount these local disks during the initial node setup. So we're also looking at ways that we can try to automate that a little bit more so we remove those manual steps. So if any of this sounds interesting to you, please try out the feature, give us feedback. And if you're interested in helping to develop any of these future items, also please reach out to me and reach out to the SIG. We can try to work in some tasks there. All right, so and in general, if you're interested in any of the either CSI or local persistent volumes or any other features related to storage, please reach out to us at SIG Storage. We hold meetings every 2 weeks on Thursdays at 9 a.m. All the details for the meetings and Zoom links are there. We're also going to have a pretty big presence at KubeCon EU. There's a number of presentations that various members of the Storage SIG are going to be giving, including some basic storage 101 intros. There's going to be a more detailed session on local storage and how it's actually used in a production environment. Some more detailed talks on CSI and also snapshots. All right, so I think that's all I have. Now it's time for Q&A.
Perfect. Thank you, Sad and Michelle. So we are ready for the Q&A session, and it's a call for all the participants here. You can see the Q&A button at the bottom of your screen in the Zoom interface. So please leave your questions right there. So the first question is regarding the DPVs, how resizing works on pod, and do we have to restart pod?
Sorry, is the question about resizing?
Right, yes. So how resizing works on pod, and do we have to restart it?
Yes, so the way that resizing works is that you update your persistent volume claim with the desired size that you want to increase to. And then the Kubernetes system is going to go and increase the size of the underlying block volume. But then in order to do the file system resize, you need to restart your pod first. And that way we can safely unmount the file system from the container and then trigger the file system resize in that case.
Perfect. The next question is, can Kubernetes post scheduling if there is a high airtime value on working nodes?
Sorry, could you repeat the question?
Yeah, so can Kubernetes post scheduling if there is a high airtime value on working nodes? So can Kubernetes interrupt scheduling when there is the high airtime value?
Sorry, there's a high what time?
I/O time. When there is a high I/O input output.
Oh, when there's a lot of latency.
Can Kubernetes scale?
No, can Kubernetes temporarily interrupt scheduling?
So I guess the question is around if there's high latency on volumes, is Kubernetes able to kind of rebalance workloads around to work around that?
Yeah, more or less, yes.
Okay.
Okay. I think so today, Kubelet is checking for a local disk I/O pressure. And if it senses that the node has a high I/O, at least on the local disk front, it's going to update the node status to say that. And I'm not actually sure if the scheduler will avoid those nodes in that case. But.
And for remote volumes, we don't really take I/O into account. So it's possible that you could have network latencies or noisy neighbor issues related to I/O. Kubernetes doesn't account for that yet.
Perfect. So the next question is probably to meet Caitlin is how can we get the slides and video stream? So this session is being recorded and will be available in the next few days at cncf.io website. So the next question is back to Sad and Michelle is about when a node is using a local persistent storage and I change the taints affinities, could this prevent the pod to be scheduled onto the node the local persistent storage was?
Yeah. So in that scenario, you can potentially have this is one of the downsides of using local storage. So if say you have a workload using local storage and it's scheduled on node A, and then you add a taint to node A that causes the pod to be evicted from it, your pod cannot be scheduled after that because it's bound to a volume that only exists on that node. So that's one of the that's one of the risks you take by using local storage. So your application really needs to be aware of these kinds of limitations, and potentially, if your application is one of these sort of distributed storage systems that can that can take a node failure and potentially restart a replica on another node, you'll have to sort of build some logic into your operator for that workload to be able to basically delete the volume from that pod so that it frees up the system. It frees up that binding to that node so that we can go find a brand new disk and bind to a new node.
Perfect. So the next question is, how can we apply read-ahead setting to the volume mounts in configuration.yaml files?
Are you familiar with the read ahead setting?
No, I'm not.
Neither of us is familiar with the read ahead setting, but maybe if you ping us on Slack, we can dig into it more for you.
Nice. So the next question is, you said that unmount volumes when resize is performed. Does the data preserved when volume is resized?
Yes.
All right. So the next question is, for encrypted disks, would it be possible to pass credentials? This question relates to a local persistent volume.
I guess it should be possible to, if you put in annotations or anything into the PVC or PV, you can pass data from that to the plugin. Right now, though, the plugin does not understand those annotations, so you would have to potentially enhance the plugin to support it.
I guess once dynamic provisioning for local storage comes out, this will become easier.
Yeah.
Yeah, perfect. Another question is, does the size of PVC or PV will depend on size of local volume disk size? Or you can curve spaces from one large local disk?
No, so each PVC can only bind to one PV. So if you want to break up one large disk, right now you have to manually partition the disk into smaller partitions and create a persistent volume for each of these smaller partitions. Right now we're working on a design to support dynamic provisioning using LVM. I think that will that'll be able to support this use case better of carving up large disks.
Perfect. So the next question is, will these changes work on Kubernetes engine or only on Kubernetes? I can answer this question. So this functionality, all this functionality that has been described in today's webinar is related to the vanilla Kubernetes. At the same time, if their distribution of Kubernetes that you're using is conformant and officially certified, so all the functionality from the vanilla Kubernetes, from the upstream Kubernetes, can be also used on that specific commercial and non-commercial distribution.
Yep.
Any other questions? We have enough time here. We have yet another question about the features. So that's the question that I can answer. So where can we find information on some other features, the 25 other features in this release? So the brief information about them you can find on blog.kubernetes.io website, the Kubernetes blog, where we are posting the latest news from Kubernetes community, including the release announcement. So please check the latest announcements from the previous week where we had Kubernetes 1.10 release announcement. And the detailed information, the raw data about the features where the Kubernetes community itself tracks the features is Kubernetes/features repo on GitHub. So feel free to check it if you need any detailed information on what's happening with the current release, with the current features in the current release, and also with the features in the previous releases, including 1.10. There is yet another question. What is that certified requirement for feature to work? I suppose that's the question about the conformance distributions. So please check the information about Kubernetes conformance distributions and CNCF GitHub webpage and github.com/CNCF/Kubernetes conformance. So you'll be able to find all the information about what are the conformant distributions of Kubernetes and how can they satisfy the requirements to be conformant. it's Kate, github.com/cncf/Kate S dash conformance. All right, so it seems that we have all the questions here. So thanks everyone for joining. Thank you, Saad and Michelle, for participating here. And I hope to see you all next week at our next webinar series related to Kubernetes and other cloud native technologies. Thanks everyone, and goodbye.
All right, thank
Thanks.
you.
Bye.